In this video, we'll talk about the phenomena of wave. Wave exist almost everywhere in nature. Some examples are water waves, sound waves, etc. And if we think of wave, I think one picture come naturally to the mind is this kind of picture. So it has some kind of periodic structure when you look at the shape. And usually that's a source of wave. So it's the point that generate all these kind of shapes that we see later on, and they all start from here. Now these wave source need to be oscillating. So let me draw some symbol here to represent that kind of oscillation. So, oops. So now let's say this point is oscillating up and down, and then that oscillation is propagated throughout the media, either water or air, that can propagate, that can support the waves propagation. And so that is the propagation of a disturbance. So that gives these waves a definition. When we say waves, it's propagation of disturbance. Because the object here, this wave source here, let's say it's not moving at all, then there's no disturbance, and there's no such propagation of wave. Only when this point is doing oscillations, then we have this wave propagating. But now let's look at this disturbance propagation in detail. So then let's think about mechanical waves. Water waves, sound waves, they're all mechanical waves. So let's start from this wave and use them as an example to talk about that mechanism. Now in the future, we're going to learn about optics. So light wave is also a kind of wave, but they're not mechanical wave. Okay, so it's a different kind of wave. So for mechanical waves, we always need a media. We need a media to propagate the wave. So for example, for water wave, the media is water. And for sound wave, the media is air. Okay, so we need something there to propagate. It cannot be vacuum. If it's vacuum blocking the mechanical wave, then mechanical wave cannot go through. Okay, so that's why we need a media here to propagate such a wave. And for water or for air, they contain particles, which is invisible to our eyes, but they're kind of microscopic particles. They're too small for us to see, but they're there. And for waters, we have water molecules. And for air, we have air molecules. So in both cases, we have some kind of molecules floating around. And now let's look at this source here. So let's say there's a wave source doing oscillation up and down, and the nearby molecules, source is kind of representation of a kind of molecule, and the nearby molecules, they're connected to the source. And if you draw the interaction between them, there's a There's bonding between them. And when this particle, the source particle, is moving, you will drag the nearby particles to move together with them. But the nearby particles, because they're being dragged, their motion is later than the source motion. So the wave source here has the earliest motion. And this particle, I'm going to call it nearby particle. They're going to follow the wave source. They're going to follow particles on the wave source, follow their motion. So that's why if the wave source is moving downward, okay, so let me actually draw a different diagram here. Here's the wave source, and that's the nearby particle. So if the wave source, these particles moving downward, that's the velocity of this particle. Then due to the interaction between them, okay, so these source particles will drag down the nearby particle. So nearby particle will follow the wave source, also move downward. And we can apply this to all particles in the media. So let's say there's another particle here. And this particle is the third particle. So you're going to follow the second particle due to the interaction between 2 and 3. 2 is going to drag down 3. So 3 is going to follow 2 by going this way. Okay. Now how about particle further away? Let's say here, particle 4. Now particle 4 is going to follow particle 3 because there's interaction between them. And 4 is going to move upward because it wants to follow 3. Right? 3 is at a position further away, so in upward direction. So 4 is going to follow that, and so on. So in this fashion, we have one by one the propagation of this oscillation. Okay, so the oscillation here is a kind of disturbance. Of course, for different kinds of wave, you can have different kind of disturbance. Oscillation is one of them. And by oscillation, we mean the simple harmonic oscillation that we studied in the previous chapter. Okay, so that is the picture that represents the propagation of wave. So now we know the particle 2 here and also 3, 4, etc. They all follow the wave source motion. And this kind of motion, right, is called the traveling wave. Because such a disturbance, oscillation in our case here, can propagate in this direction with some speed. We're going to talk about that speed later on. This speed is different from the V1, V2, V3 before we talk about. They are actual particles velocity, and they're not this V here. This V is called wave speed. How fast the oscillation motion is propagated. It's called V. So now let's look at one detail string wave. Look at one string wave in detail, and let's think about what kind of mathematical equation that governs the wave propagation. Now for a string, let's say we're looking at this 1D system, which is a string, and let's say we apply a tension force on both ends of the string, and we're at equilibrium. The string is at equilibrium. And these two tension forces are equal in magnitude and but opposite in directions. Now, if I look at, let's say, the left end, this small string here, and I will use this end as the wave source to do oscillation. Then its oscillation around this line, this horizontal line, is simple harmonic motion, and it's going to propagate along this string here, right, along this direction. Okay, and this position, the dashed line here, is called the equilibrium position. Now, all the oscillations are with respect to this line, not just for the wave source, this point, but also for any points later on when they oscillate. They will use this dashed line as equilibrium position. Okay. Now, in the previous picture, the dashed line will be this line, is this line here, and that's the equilibrium position. Okay, so naturally during the wave propagation, we have this vertical displacement from the equilibrium position, and we want to build a coordinate system for that direction. So this direction, I'm going to call it a y-axis, and the horizontal direction along the wave propagation, I'm going to call it the x-axis. So it's kind of like a two-dimensional system. The oscillation is along y, but the propagation of the oscillation is along x. Now with that, think about one section of the wire during the oscillation. Let's say I'm looking at this section here, okay? So this section, that's the wire. String section, sorry. Now let's say it has mass, let's say delta m, a small mass delta m from here. Now, if I look at the left side and right side, there are two forces acting on them. Let's call this F1, and let's call this F2. Okay, the left side is F1, right side is F2, and they're acting on this small section of the string. Now, if I decompose this force F1 and F2 into the two directions, x and y directions, then we get tension force for both forces in the x direction, and they must be equal because we apply at the two ends of the string two tension forces in the opposite direction, and they should cancel out, and the string has no motion along this direction. So one key thing here is no motion along x, and that means that we're at equilibrium condition. Or the net force along x direction must be 0. So that's why these two components must be equal. And we call them T in the previous diagram. Now in the y direction, there's this f1y and f2y, right, acting on the string in y direction. And in this y direction, we cannot say the string section, the small section here is at equilibrium, because they have acceleration, they have oscillation, right, in this direction. So that's why we should write down Newton's second law for the y direction. So the net force in y direction equals F1y minus F2y, and that equals delta M over AY. Delta M is the mass of the string section, of this small string section. Let's think about what can be done here to the Newton's second law's equation. So we know these two t's are the same in the horizontal direction. So now if I say this angle or this angle here is theta 1, and the other angle here is theta 2. Then we have f1y over t equals tangent theta 1, and f2y over t equals tangent theta 2. So we can replace the two forces on the left side by t times tangent theta 1 minus tangent theta 2 equals delta M over AY. Now our purpose here is to get an equation that contains the displacement y, let's say for any point. That's a y displacement. And also the relation with x, the position x, and also the time. So we want to do something here for the two tangent angles. So tangent theta 1 is y delta y over delta x at position 1. Tangent theta 2 is delta y displacement over in y direction over delta x at point 2 at this end, the other end. Now if I do the subtraction here, then I get, we continue next page. So I get delta y over delta x 1 minus delta y over delta x at position 2, and that equals delta M times AY. Now I want to do something. I want to multiply, I want to divide on both sides delta x. Okay, so let's look back at the picture. So if I think about the length of this string section, its mass is delta M and its length is string length. Should be delta x, right? Because it's measured along this x-axis direction. So that length here is delta x. So if I divide it by delta x, on the right side, I'm going to get a linear mass density. Let's call it mu. The delta mu here equals delta M over delta x. So its SI unit is kilogram per meter. That's mu's unit. Now with that definition, then the right side becomes mu over t. Okay, so I also divided t on both sides. So the right side get a t here. And dy here is the second derivative of position y, the displacement y, with respect to the time. Now the left side, because I have delta y over delta x, in the limit of delta x goes to 0, we get partial y, partial x. Okay, so that's the limit of delta x goes to 0, we get this ratio here becomes partial y, partial x. Now we have partial y, partial x at position 1 minus position 2, and then divided by delta x. Again, in that limit, so we have partial y, partial x at position 1 minus partial y, partial x at position 2, and then delta x in the limit delta x goes to 0. So now we're looking at the second order ratio here. Now that becomes the second order derivative of y with respect to x. So that's why on the left side, we take this limit, partial y, partial x squared equals mu over t times partial y squared, partial t squared. Okay, so this equation is the wave equation, differential equation on a string. And in fact, this one is general. We can generalize to any wave system. Then we have this so-called standard wave equation equals 1 over v squared partial y, partial t squared. Okay, so now v here is called the wave speed, and it represents how fast the oscillation is propagated throughout the media, and it's not the speed of the particle. Okay, so let's look back at the previous picture. So when I label these v1, v2, v3, v4, etc., they represent the velocity of the particle, the actual velocity of the particle, the oscillation along this y direction. Now this v here is the wave speed, and it represents how fast the shape here is propagated to the right. Okay, and in a wave propagation, particles do not move. Particles in the media, they do not move along the x-axis. Okay, they oscillate in the y direction. So that's why in the future, when we mention the particle's velocity, we're going to say Vy. Okay, and we reserve this V without the subscript as the wave speed. Okay, so that's why we have this standard differential equation to solve for next time. And we're going to talk about a solution to this differential equation and the meaning of the solution. Okay, and that's all for this video. Thanks for watching.